Higgs International Conference. And we have the pleasure to have with us Professor Manuella Vincter. She will tell us about everything, I would say. So from the extremely small to the extremely large. Professor Manuella Vincter is a research professor in physics at Canada, at the Carleton University, and also a fellow at the Royal Society of Canada. She mainly works in the Atlas experiment, where she's a deputy spokesperson and a very good friend of the Portuguese group at Atlas. And she will basically help us and guide us through this wonderful world of the origins of matter and how everything works. But I will pass the word and listen delightfully as well. So thank you very much, and please go ahead whenever you would like to. I would like to remind people following us on YouTube that they are very welcome to write questions on the chat. If they prefer to write in Portuguese, they can also write in Portuguese, and we will translate it to Professor Vincter. And I think that's basically it. So let's just get started. Thank you very much.
Thank you very much. Let me share my slides here. Here we go. Okay. I hope that I'm sharing my slides.
Yes.
Okay, very good. All right. Hello, everyone. It really is a pleasure to be here today. And I want to thank the organizers for inviting me to give this lecture, this public lecture, on the relations between high energy particle physics and the scale of the universe, from the infinitely small to the infinitely big. I wish that I could be with you in person. If it were a conference, if it weren't for COVID, I would be there in front of you with my little name tag so you could see my name. My name is Manuella. I'm a professor at Carleton University in Ottawa in Canada. It's the capital of Canada. You can see here a picture of my beautiful campus nestled between a few little rivers there. I'm an experimental particle physicist. I'm also the deputy spokesperson of a very big international collaboration called Atlas, and this is based at the CERN laboratory in Switzerland. So throughout my talk, I hope I'll be able to address all three of these points that are in red so that you'll understand what I mean when I say this. Before, I want us to step back a little bit and just say that the universe is really beautiful. I mean, we have to take the moment to enjoy this, especially after COVID confinement, so that we all appreciate and realize just how beautiful it is, and that this beauty encompasses enormous scales, from the infinitely big, where you see here a beautiful picture of this Horsehead Nebula, which is only 1,500 light years away, to something that is infinitely small, like this picture of neurons that are associated with cells that are only 10 micrometers. So really beautiful to look at, but also beautiful to contemplate in terms of distance scales, because it really is mind-boggling, the distance scales of the universe. So I want to spend a little bit of time to just explain to you what I mean by that. All right, so let's look at the universe. So as we know it, the universe came into creation about 14 billion years ago. It started off with a big bang, was a very hot explosion. And as the universe aged and cooled down to where it is today. And so now the size of the universe is estimated to be something like 10 to the 27 meters, which is a really big distance scale. If you want to come a little bit closer, you can have a look at the Milky Way. This is the place where our own star hangs out. And this Milky Way is something like 10 to the 21 meters. Inside the Milky Way, you'll find our solar system. So our big, beautiful sun and all the planets. And of course, Earth is the third planet from the sun. And the size of the Earth is about 10 to the 7 meters. So now we've gone from 10 to the 27 to 10 to the 7. So this is what we call 20 orders of magnitude, or 20 zeros in terms of number of zeros for describing in meters. Now, right here in front of you, probably you're sitting in front of your laptop, and your desk here is about 1 meter in size. If you could start taking your desk apart to find its fundamental constituents, you would go to atoms with electrons. And then at the center of each atom is the nucleus, so very hard core. And then the nucleus itself is made of protons and neutrons. So when you go now from the nucleus to the proton, it's about a factor of 10 smaller. So now we're at a distance scale, which is 10 to the minus 15 meters, where before we had positive values. Now this is very small indeed. And in fact, the proton itself, as far as we know, is not a fundamental particle. It actually contains other things, one of them being something called a quark. Now here I say a distance scale of less than 10 to the minus 18 meters. It's not because I know the size of the quark. It's just that if the quark has a size, then it has to be smaller, that number, because we just don't know what is the size of a quark. So it's very, very tiny indeed. Now, through all of this, I've been using something called scientific notation. And you may appreciate now why I like to use this. So these 10 to the number up there, because if I have 1 meter, which is my table in front of me, if I go to the distance of the universe, and I want to describe it in meters, it's 1 with all of those zeros, meters. And now if I want to talk about these distance scales, then it's point, and then all of these zeros here, and then you have a 1. So there are in fact 44 zeros that tie the size of the universe to the smallest things that we know of in the universe. So that's why I mean it's really mind-boggling, the size of the universe. You might recall from the days when you were in high school, maybe you did a little bit of basic science, maybe you did some chemistry at some point, where you discovered the periodic table of elements, the table that tells you, hydrogen, helium, where it is on this table. And you were told that all of the universe is made up of these atoms. So here's a picture of an atom, or a diagram of an atom, again, with the nucleus, with the protons and the neutrons on the inside, and these electrons whizzing around. Now, and I just told you a moment ago that the protons themselves are not fundamental. So this little diagram that I gave here for the proton is just a very schematic little diagram. In fact, the proton on the inside is very complicated business. It's made of all these other objects called quarks, and also the gluons, which are the things that keep the quarks inside the proton. So all the universe is made up of this, right? You were told this in school. Well, I'd like to challenge this, because you soon realize that's probably actually not quite true. So the universe is not just made up of these atoms. And the way I'm going to try to explain this to you is to introduce you to this beautiful galaxy called the Triangulum Galaxy. It's a spiral galaxy, so all the stars go around in a pattern that's a spiral, and it is about 2.73 million light years from Earth. It means that if somebody is in that galaxy would turn on a light bulb, it would take 2.73 million years for the light to reach our eyes. So that's a very far away galaxy. And the galaxy itself is actually very big. It's about 60,000 light years across. And this one galaxy is estimated to contain about 40 billion stars. So again, these large numbers, large distance scales, 40 billion stars in one galaxy. And by the way, the Hubble Space Telescope, which is a telescope which is in outer space, the astronomers use that information to estimate that there are about 100 billion galaxies. So 100 billion galaxies, and each one of them containing millions or even billions of stars. So there's a lot of stars out there in the universe. There's a lot of matter out there in the universe. Okay, so this is the Triangulum Galaxy. And I want to introduce you to someone, Louise Volders, who in 1959, what she did is she wanted to measure how fast stars go as they go around the center of this Triangulum Galaxy. So here's the picture of the Triangulum Galaxy again. This is sort of a picture where we're looking out a little bit. And so each of these stars go around the center of this galaxy, and they all go with a certain speed as they go around the galaxy. And she had an estimate, just how fast these stars should go. And this is an estimate which is based on something called Newtonian mechanics. And Newtonian mechanics is, maybe you don't know what it is, but if you have a dog, you know everything you need to know about Newtonian mechanics. Because as you know, dogs, they love to chase things, so you love to throw a ball at them, Or you might like to throw one of these flying discs at them, so you throw the flying disc, and as you throw the disc turns around, and then the disc the dog catches the disc. And some of you might have played around with different discs and might realize there are two kind of varieties of discs out there. There are these discs that are solid through, so that the mass is everywhere on the disc and uniformly distributed. And there are other types of discs where the inside of the disc is hollow, in fact, and it's just a ring. So you throw the ring. And if you throw the ring or the disc to the dog, and if you practice a few times, you realize that the way that you have to throw the disc in order to reach your dog is different depending on which one you have in your hand. And the way it spins as it goes from you to your dog is going to be a little bit different again. And the reason for that is just that the mass of your disk is distributed in a different way. So either in the center of the galaxy or in center of the disk or on the outside of the disk. So using this is Newtonian mechanics. She had a good estimate of how the velocity of stars should go around this galaxy. So if the stars were very close to the center of the galaxy, she estimated that they would go very fast. And as you would go further and further away, if you took a star, say on the outside of the galaxy, you should go much more slowly. So this is what the shape would look like as a function of where you are in the galaxy. But then when she measured it, she saw something was completely different. She saw that the velocity or the speed of these stars is independent of where you are in the galaxy. It's pretty much flat. And this was really shocking to her and to the community, because if you sort of thought about it, you think, okay, this is a galaxy, lots of stars, there's gravity involved. So if you really had stars that were traveling at that speed around the center of the galaxy, this galaxy should not exist. It should have blown apart a long time ago. And of course, the galaxy is still there. So obviously there's something wrong with that assumption. And a possible explanation was maybe there's missing matter in the galaxy. And the analogy is maybe she was thinking, it's like she was thinking the galaxy was like one type of disk, when in reality, it's the other type of disk. And this missing matter in the galaxy would have to be something that you can't see with your eyes. Because the way she estimated how much mass there was in the galaxy, she looked at the number of stars. She sort of made a guess as to how much each star should weigh. And then she could come up with an overall mass for the galaxy. All right, so now we think that there's actually missing mass in the universe. So because this galaxy tells us that it looks like there is missing mass. There's another way that you can look at information to tell you a little bit about what is the breakdown of all the mass in the universe. So remember I told you that the universe originated 14 billion years ago. It was a very hot explosion, and then it sort of cooled down as a function of time. Now the galaxy is actually quite cold. If you were to go out in outer space, we estimate that the temperature of the galaxy is something, not the galaxy, but the universe is about 2.7 degrees above absolute zero. So it's very cold. This is a map of if you were to look out into the sky and of the temperature that you would see. And so some places are a little bit more than 2.7 degrees, some places a little bit less, but more or less that's what it is. And based on this kind of information, you can turn this information around and figure out what makes up the universe in terms of all the energy and the mass in the universe. If you look at this map and you interpret it, you realize that in fact, less than 5% of the universe is the atoms that you were told in high school the whole world is made up of. So it's less than 5%. So what's the other 95% of the universe? Well, there's some other component, which is about 23%, which is the dark matter, which could very well be what Louise Volders was noticing in this triangular galaxy that was missing, which she couldn't see, but was impacting how the stars were turning around. And then there's this other big chunk, which is dark energy, which nobody really knows what it is, actually. We don't really have any viable, let's say, evidence for what it is. We know that it's there, but we don't know what it is. So today, I'm just going to limit myself to this slice of the universe, about 25 to 30% of the universe. But it just goes to show that, most of the universe, we still don't understand what it is, which is really surprising. So let's focus a little bit on this dark matter here. We know that we think we know that it exists in this triangular galaxy. So probably it exists also in our galaxy. Why would it exist somewhere else but not here? So how can you find this dark matter in the universe? One way that you can do it is, since you know, or you think you know, it exists in this galaxy, you could just build a piece of equipment that would be very, very sensitive and try to measure it. That's very hard to do, but it's certainly an avenue that people are taking to try and do this. Another way to do it, and this is what I'm going to be talking about, is if I can't find the dark universe and the dark matter in the universe, why don't I make it myself in the lab and study it under controlled circumstances? So this is the lab where I work at, which is called the CERN laboratory. It's on the Swiss-French border. It's in Geneva, in Switzerland. It's a fabulous lab. It is really a paradigm for international cooperation because it has many countries that participate, scientists from many countries. I'll tell you about my own experiment. And, there are about 100 different nationalities of people who collaborate in my experiment alone. And in this laboratory, scientists do come from around the world, and they try to find the answers to these fundamental questions like, what is the missing mass in the universe? And they use particle accelerators and really leading edge technology to try and answer those questions. So I'm going to try to talk to you a little bit about some of these aspects. First, I'm going to talk to you about the accelerator, which is at the CERN laboratory. It's called the Large Hadron Collider. I say here that my little byline is discovering the early universe, and you'll see why I'm trying to say that because in the laboratory, we try to reproduce what happened just shortly after the Big Bang. But this accelerator here is a proton accelerator. So protons go around one way. You can see this big ring here. This is the accelerator. Protons go the other way. This whole ring is actually 100 meters underground. These protons travel at almost the speed of light. We accelerate them to be 99.9999991 times the speed of light. And then when they reach essentially the speed of light, then they collide in an experiment, and we look at what happens, what comes out of the collision. This is the CERN laboratory right here, by the way. Now, you may ask, why do we want to collide protons to make energy, right? Well, remember I said that the early universe was very hot. So hot means energy. So you need energy if you want to reproduce the early universe. And we all know this face here. We've probably seen them on posters and T-shirts, and maybe you've even seen this equation, E is equal to mc squared. This is his equation here. But actually, it's a very profound equation. This equation says that if you have energy E, then you can turn it into things that have mass m. So these high energy proton collisions, what they do is they provide the energy which can be converted to new objects. So protons, matter, they collide to produce energy, and then this energy can make new matter that hasn't existed since basically shortly after the Big Bang. And in fact, the LHC is probing the time, which is less than a billionth of a second after the Big Bang. So it's a very, very short period of time after the Big Bang. So this big collider has a lot of energy associated to it. And in fact, the energy associated that's stored in each beam is 360 megajoules. It's a unit of energy, but maybe I can convert it to kinetic energy. So it's the equivalent of the energy of 450 cars traveling at 100 kilometers an hour. It's the energy of 70 kilograms of chocolate if you were to count the calories. I was pretty shocked to see that, it's 70 kilograms of chocolate. So that's obviously a lot of chocolate. Or it's the equivalent, the thermal equivalent of making 1 ton of tea. So it's a lot of energy. All right, we want to collide protons. So the first thing is I need a proton before I can collide it. Now I can't go to the store and buy protons. They don't exist. However, I can buy hydrogen at the store. This is a very simple atom because a hydrogen atom is just a proton and an electron. So if I buy myself a bottle of hydrogen, I can take the hydrogen out and I have the ability to just strip that electron off. And now I'm just left with protons. So these protons will get injected into this chain of accelerators that I'll show you in a second. related to the LHC, and every time they go into a different accelerator, they go faster. So they start off very slow, and then they go faster, and then faster, and then faster until they reach basically the speed of light. So let me show you a little diagram here. Okay, so here's the first accelerator. You can see now two bunches of protons. They go to another accelerator and they go faster there. Then they go into the next one, which is called the SPS, and there they go even faster. And then finally they enter the LHC, where they go basically at the speed of light. And now I'm going to take you for a little view down inside the LHC. So now you're 100 meters underground. You can see this big tube here. It's inside this tube that the protons travel. So it's a tube that's in a vacuum. Here are my protons. You can see the three little quarks hanging out there. They're going really fast. And you can see one set of proton here. And on the other side, we're going to see another bunch of protons appearing. Here they are. And then the two bunches of proton collide in the center of my experiment. Proton turning to energy, turning to new particles. And these new particles are shown by these white lines. Basically, they just show the path that the particles take after the collision. And all the colorful stuff on the outside is just a representation of a detectors that is needed in order to see what's coming out of these collisions. So LHC provides the collisions. Now you need a bunch of cameras to be able to see what came out of these collisions, right? So you have collisions, and then out come the new particles. And so you need a camera, what we call them detectors, that basically can follow the path of these new particles that came out, and also measure the properties of the particles that come out. So for example, you see these squares here that are sticking out. The size of the square is just proportional to how much energy that particle had. So for example, here you see tiny squares, so the particle's not very energetic. Here you see big ones. And so that gives us more information about the path of the particles, how much energy they had, and it allows you to interpret what it was in the first place. So these detectors or cameras that take pictures of each of these collisions are very special cameras. I can't use my phone here because this camera needs to take 40 million pictures per second. And when the LHC is running, the LHC runs 24 hours a day, 7 days a week for about 9 months a year. So it's just perpetually taking lots of pictures. So in fact, the LHC has 4 such detectors or cameras. The 2 here, Atlas and CMS, they're the ones who are kind of all-purpose type cameras. They're supposed to do everything. They could do precision things, they can discover new science. Then the other 2 are very dedicated in the sense that they're looking for very specific type of physics outcome. So these are dedicated objects. I'm going to just briefly tell you a little bit about Atlas because that's the experiment that I work on. So Atlas is 100 meters underground. It's just a sketch of it. It's very big. So you can see here this tiny little person. Yeah. And so the whole detector here, if you were to go outside and look for a 7-story building, wherever you happen to be in some downtown somewhere, that's roughly how tall this detector is. It's 7 stories high. It's very heavy. It's about 7,000 tons, which is roughly the same amount of iron that went into this lovely tower here in Paris. So it's a very heavy object as well. So Atlas is like a camera, a giant camera. And just to remind you, the protons come in from either end, and then they collide in the center of the detector. And from that come out all the new particles that you want to study. This is just a visualization of one of these collisions. So this visualization, what it does is it shows you what it looks like after the collision. So at the center here is where you had the collision. And then as the particles are created, they expand out. And again, the lines show the paths of the particles that came out. And then the size of these squares tells you, how energetic each of these particles are. So we do a lot of these visualizations because even though we do a lot of analysis related to computing with computers, and we also like to see with our eyes, what we're actually producing. Now, the most important aspect of the experiment, actually, and it's a secret weapon to success, is actually the people who work on this experiment. If you would believe it, there are 6,000 people that work on one experiment, on my Atlas experiment. These are people from across the world. They just use this to do science, and they can be professors, they can be experts, in computing, could be technicians, engineers. In this experiment, we have 1,200 PhD students alone. So it's a great place for training ground for our PhD students. And we really need people of all kinds of interests and skill sets to do everything that we need to do. So some of us, we like to build new parts to the detector. So we said, okay, this part is not good enough anymore. We want to improve. We want to build a better detection, so improve the camera effectively. Some people spend time just repairing of the detector, because the detector has a very long lifetime. Every once in a while, you just have to go and repair things. Some people also like to be in our control room, so to be able to see the collisions as they come and record this information. And we also like to meet as a community. Most recently, because of COVID, we've had to do a lot of these Zoom meetings like we're doing today, but we also like to meet in person, and we're looking very much forward to the end of COVID for many, many reasons. One of those is so we can finally get together again and see all our friends and colleagues. Before I go any further and tell you a little bit more about the science that comes out of the LHC, I think I should spend just a few minutes telling you what's the underlying science that we want to do with these collisions. And the way that I'm going to do it is I want to introduce to you the 4 fundamental forces of nature. The one that you may be the most familiar with is gravity. This is, of course, what keeps the Earth going around the sun going around the galaxy, or going around the galaxy. And it's what's keeping you in your chair right now. It's actually the force that we know the least about, by the way. Then there's another force called electromagnetic. That's the force that's responsible for electricity and magnetism. Then there's another one called the weak nuclear force, which you may not be so familiar with, but it's actually part of your everyday life. This is the force that is responsible for the nuclear burning of the sun. Without the weak force, we wouldn't have the sun burning. So it's very important. The fourth one is called the strong nuclear force. Again, you might not think you're so familiar with it, but it sure is part of your everyday life. This is the force that keeps the quarks inside the protons inside the nucleus, and the nucleus, so that we have atoms. So without this, we wouldn't have atoms. And of course, without atoms, we would not be here today. So it's a very important force. Now, when I say that there are 4 fundamental forces, I mean that if you can think of any other force out there, it's not a separate force. What it is just kind of a manifestation of one of these 4 forces. So as far as we know, there are these 4 forces. I want to mention one more thing which is important, and that is the Higgs boson. The Higgs boson, I'll mention a little bit more in a moment, but the Higgs boson is kind of a manifestation of the mechanism that has given mass to everything that is around us, right? Anything that has mass is through this Higgs mechanism. All right, so we have on the one hand all this matter in the universe, the electrons, protons. On the other hand, we have these 4 fundamental forces. And somehow when you have 2 bits of matter next to each other, they know that they're each other, that they're near each other. I mean, another way to phrase it, when you fall, you always fall down. How does it that your body knows that the Earth is down there and it's not over there? Why don't you fall up, for example? So somehow the 2 bits of matter are able to know that they're near each other somehow. And I'm going to explain a little bit how they do that. So I have a little diagram here of 2 electrons, and 2 electrons know that they're near each other. And how they communicate with each other depends on what force we're talking about. So here are my 4 fundamental forces. And so if I'm talking about the electromagnetic force, the way that an electron talks to another electron is by exchanging little carrier pigeons, little messages. So these messengers are photons, here, gamma, if it's electromagnetic force. If it were the weak force being exchanged, then it's a different type of messenger. In this case, it's something called the Z. And gravity, for example, is also, I mean, the electron has mass, right? So electron, just like the moon and the sun, should be able to interact gravitationally. We think it's done through something called gravitons, but I put a question mark because we've never actually seen a graviton. This is our supposition. And the range over which these forces act on matter depends on the force. So here, you just say infinity. I mean, if I were to take two electrons and bring them across the galaxy, in principle, the two electrons still know that each other are there. So they can still exchange information between the two. But that's not the case for the strong and the weak force. The strong force only acts within roughly the something that is the size of a proton, is very small. So anything bigger than that, like they don't interact with the strong force. And through the weak force, it's even smaller. I mean, the weak force only acts on things that are inside the proton, roughly at the quark level. So that's how matter and the forces interact with each other. Now, you may have sort of caught this, and it's just like, if it's a fundamental force, why are there four of them, right? Why can't we have, one fundamental force? Why is it four? Well, that's an interesting question. And we think we have an answer to that. And I'm going to show you this diagram here. This is kind of a diagram where it's like time, all right? So down here, this is today. Today, we see these four fundamental forces. If I go up this chart, I'm going back in time. And remember, back in time means closer and closer to the Big Bang, which means hotter and hotter until I get to the Big Bang, which was super hot. Now, if here in this room, I can tell you there are four fundamental forces. If you could go back in time or hotter, you would actually see that two of these forces actually combine to be one single force. This is the energy that the LHC operates at. So in fact, here in this room, I can tell you we have four fundamental forces, but when we work at the LHC, I only think of it as three fundamental forces. Now we have a good expectation. We have, let's say, indirect hints that if we could go even earlier in time, so hotter again, these two forces would merge into one force. And if we could go super early in time, and I mean really early in time, this is 10 to the minus 43 seconds. In fact, there was only one fundamental force. So as the universe expanded and cooled, you went from 1 to 2 to 3 to the four fundamental forces we have today. So that's why we think, 4 is not a crazy, I mean, that's what we observe, but in fact, it probably was 1 at the beginning of time. All right, so I'd like to just go through a little bit about the kinds of things you would see at this conference this week. So I'm here talking to you today because I was kindly invited to talk at this PANIC conference. And this PANIC conference is a conference that should have been in Lisbon. And this week is hosting virtually nearly 600 physicists from around the world. So I just want to go through and just show you the kinds of things that you would see if you were a physicist attending this conference. Oops, I'm on the wrong page here. There we go. So the first thing you would see a lot of these things. These are visualizations. So we call them event displays, but you've already seen one before with the lots of yellow, but this is another visualization. In this picture, you can see here, the proton would be coming this way, the other one the other way. Here they would collide at the center. And what you see is all the particles that come out. This is a beautiful event display. Actually, this is a display that shows four types of a quark, 4 quarks of a certain type being produced at the same time. And this is a very special type of quark. Didn't go into too much details about quark, but this is the heaviest quark that we know about. And in fact, it's something like 200 times the mass of a proton, just one quark. So you got 4 of them. So this is a really spectacular visualization. Then you could sort of divide what we do into 2 rough branches of science. So the first thing is we search for things. So we search for new phenomena. So we search for either we just, we don't want to bias ourselves. So we're going to look for anything that's out there that's new and unexpected. That's one way to search. The other way to search is we can have our theory colleagues who can come up to us and say, look, I have a theory. I think it's well-founded. I think that if you were to look for this, you might see this new phenomenon, or you might see this new particle. So we look for new particles. Unfortunately, we found very few new particles, but we looked for them anyway. And so we show a lot of plots like this. So let's say I looked for a new particle, but I didn't see it. So I would then say at this conference, I've looked for the particle, I haven't seen it. And if it does exist, its mass has to be greater than some number. And what do I mean by that? It's, well, either I looked for it and I didn't see it because it doesn't exist, or maybe I looked for it and I didn't see it just because my equipment is not sensitive enough yet, or I don't have enough information, enough collisions to be able to see this new particle. So in a plot like this, which would be the mass of this hypothetical particle, and it's a whole bunch of values, because I don't know about what the mass is. I've never seen this particle before, so I have to probe possible values. And then often on this side of the plot here would be some other property of this particle so that I could tell what it is more easily. And then I would end up having a plot where it says, well, I looked everywhere here and I can for sure exclude that this particle exists if it lives in this space here. So if its mass is up to, say, maybe 800. And then on the other side, it says, well, this is still to be discovered. If it's there, I can't be sensitive to it. And maybe at a next conference, somebody will bring us more information. So there we search and we don't find stuff. Then sometimes we get really lucky. Doesn't happen often, but we get really lucky and we search and we discover something. Now, this is a very special plot, actually, in our hearts. This is the plot that was related to the discovery of the Higgs boson 9 years ago. So when the LHC started, we had a really good expectation, let's say, that this particle should exist. We had never seen it before, so there's no evidence. We had a good expectation that it should exist. And in fact, it was a really key particle because we have this beautiful framework that explains, nature, how we think nature works. And there was one big missing piece right in the middle of it. And this missing piece was this particle. So we searched for it and we saw it. So you will see plots like this, which is the mass of this new particle. In this case, it was the Higgs. You can see this blue bump here. This is how many times, basically, we've seen this new particle when we were looking for it. So we saw it quite a few times. And its mass is about 125 of these units called GeV. And this was so important that the people who postulated its existence, so the theorists who postulated its existence in the 1960s, actually got a Nobel Prize because we found it. The final type of physics that we do at these conferences, we try to measure things with really great precision. So things that we already know, but maybe with not such great precision. And why would we want to measure something that we already know? Well, the beauty of this is to measure something incredibly well. Then you compare it to an expectation. So what you think you know about that particle, which you also want to an expectation that's very good. So compare what you measure with what you expected to see. If they agree, then that's great. It means that you understand the underlying science below it, and that's good. And you've learned through this measurement to understand it even better. However, if you measure it and then you compare it to the expectation and it doesn't agree, one of two things happen. Either you made a mistake in your measurement, which we hope we didn't do, or maybe you don't understand the underlying science as well as you thought you did. And if you didn't understand the underlying science as well as you thought you did, that's another way of discovering new science, new phenomenology, new things that you didn't know about. So that's one of the things I really love to do, is to do these really precise measurements and comparisons, because I'm always hopeful that I will find differences between what I expect and what I measure, which will tell me something new about the universe. So here's a plot here of a mass of a particle that is well-known particle. It's called the W particle. It's the messenger that I was talking about that's related to the weak force. This is the expectation of it. So it's the value, and every expectation always has some uncertainty associated to it. And then all these previous measurements, and this is the most recent measurement from Atlas. And it was interesting because there was a little bit of tension. This is what we expected to see. And then the previous measurements, although the uncertainty was very large, there was a little bit of difference. But so far, Atlas seems to be really agreeing well with the expectation. Now I should come back to this dark matter that I talked about in the first place, and trying to see this dark matter in the LHC. So the first thing you would ask is, how can you see something that you can't see, right? I mean, in this triangular galaxy, we knew we could guess that there was extra matter there, dark matter, but we couldn't actually see it with our eyes. So this dark matter is thought to be something called weakly interacting. So it doesn't emit light, so it's not subject to the electromagnetic force, and in fact doesn't interact with most of the forces. But even though, I mean, it's hard to see it, it is a particle, and it's still subject to the same laws of physics that all other particles are subject to. So laws of physics meaning, conservation of energy. If you have so much energy at the beginning, you got to have the same kind of energy at the end. Conservation of momentum, which is related to the mass and the directions and the velocities. Like when you play pool, billiard, conservation momentum there. So what I want to do is I want to just illustrate to you how you would go and find dark matter even without seeing it. So I'm going to show you two just little cartoons. I'm going to first of all have two protons that are going to collide, and out come two particles that I can see. So here we go, they collide, and out comes two particles that I can see, two green particles. Now, this is a very well-defined system in the sense that I know that I had two protons going in. I know, how fast they were going, and then I should know very well how they're coming out, just like playing pool. Now I'm going to repeat this, but instead of having two green particles that I can see coming out, I'm going to have one of them being dark matter. So how we have protons that collide, out comes one particle that I can see, and the other one is dark matter. I can't see that. I mean, I put a little dotted line so you can see it, but you can't really see it. But this one went off knowing full well there's another particle somewhere, right? So it obeys the laws of physics, energy and momentum. So even if I can't see this, I can measure this. So I can infer that the dark matter existed if I can measure this. So what I'm looking for are actually particles that seem to recoil off against nothing at all. And here's a beautiful display, a visualization of something that shows exactly that. Let's look here. So again, your proton comes in this way, another one comes in this way, there's a collision, and then out comes this big, beautiful particle that I can see, and lots of energy. And then on the other side, I put this little dotted line here to show you that there's actually nothing there. So it is a particle that I can see that recoils against nothing at all. So that's one of the ways that we can look for dark matter is not, you don't see the dark matter, but you see the stuff that comes with it. Now, seeing this picture, you might say, hey, Nobel Prize time, we've just discovered dark matter. This is a beautiful picture. Hey, it's great. The problem with that is that there are already known particles that we're very familiar with that look very much like dark matter particles. I mean, they are dark matter particles, but they're the kind that we already know about. We want to know about the stuff that we want to see the stuff that we don't know about that would explain this triangular galaxy. And so the nature already produces these particles called neutrinos, and they behave just like dark matter, right? They don't interact much. They're very abundant, though, actually. Most of them right now are coming from the sun. And in fact, where you're sitting right now, believe it or not, about 100 trillion of these neutrinos are passing through your body every single second. But they're what we call weakly interacting. They just go through you. They don't even know you're there, right? And you don't even know they're coming through. So before I can compare what I saw in my experiment, what I need to do is I need to account for all other possible sources of things that look like dark matter, but are not the kind of dark matter that I'm looking for. So you might see in a conference like Panic, some distribution that look like this. So on one here, I have something called PT recoil. It's just a quantity that's characterizing how this is moving off on one side here. This the particle that I can see. And then the black dots are how many I saw of events, like I just showed you, for example, as a function of how fast this particle is recoiling off. All right, so what I see is in black. And then all these colorful things that are stacked up on each other, these are all possible sources of these neutrinos, all kinds of things that have neutrinos in them. So I know about them. They're annoying. They're hard to see, but they're annoying. And so basically, I need to account for them all before I can see anything that is new. So if I want to find this new dark matter universe, I need to compare what I measure in black with what I expected in the first place. And if there's any difference between the two, then that could be my dark matter that was missing. And unfortunately, you can see when I take the ratio of the two, it's 1. So unfortunately, we haven't actually seen anything related to this dark matter yet at the LHC, though we hope to see it. Okay, let me try and wrap up here because I'm running out of time. What's next for the LHC? Well, I told you the LHC is this a proton collider, but it's been running for quite a while. Our very first collisions came in 2010. And the way the cycle is, we run for 3 years, almost nonstop. Then we take a little break for 2, and then we run for 3, and then we take a break for 2. And of course, during these breaks, we repair and improve. Now, there's a very important era coming up for us in about 6 years or something like that, which is called high luminosity LHC. And the reason for this is that the LHC is going to be really, really improved, such that we have so many more collisions than we have now. So right now, when we collide protons together, we never take like one proton and collide it with a second proton because they're so small. If you try to collide them, they would never cross each other. So what you do is you take a whole lot of them. You take like actually 100 billion of them with 100 billion, and then you get them to go through each other in the hopes that a few of them collide. And in fact, in this early era here, we could do 10 or 20 of these collisions simultaneously. Nowadays, so run 3, which is going to start next year, there are about 50 or so of these collisions at a time. But in this HLLHC, we expect to get 200 at a time. So this visualization is a kind of a nice visualization. It's not a real data event. This is a simulation, so it's a computer that created for me. It's showing the same event and what it would look like if you had seen this event basically here at run 1, if you see it now, and the way it's going to look like at the LHC. So old, recent HLLHC. So you can see that the picture is becoming really complicated. However, the amazing thing about the HLHC is we hope that when we're in this era, we're going to accumulate every year as much information as we accumulated in the whole 17 years that led up to this moment. So it's a very special moment for us. So we already need to start thinking about the future of RMG collider physics. I'm going to show you these projects have incredibly long scales. So the LHC in this experiment, the first thought, so the seed of an idea, came sort of in the mid-1980s. It took about 10 years for this to sort of solidify and to have the LHC and experiments being approved. So the LHC experiments like ATLAS was approved in the mid-1990s. Took us then another sort of 8 years or so before we could start having equipment appearing in our experimental area underground. And the first collisions was in 2010. These high luminosity collisions that we expect are going to come in the 2020s. And then the end of the program should be probably around 2040. So from start to first collisions, it was 25 years. From first collisions to the very final collisions at the LHC will be another 30 years. So it's 55 years. This is several careers, actually, of people. There's nobody in this who will have seen it from the start and to the very end. It's just too long. So if the LHC is to have a successor, we need to start thinking about it right now. And in fact, we are. The European community has been getting together and looking at high priority initiatives. So they're still at the stage of possibility, so they haven't made concrete decisions, but they have come up with kind of a two-pronged strategy when it comes to collider physics. The first thing they want to do is the so-called Higgs boson factory. So it'd be a collider, like a proton-proton collider, but instead they would be colliding electrons. And this factory would produce so many Higgs boson that you would be able to do really precision measurements, like so precise that you could confront what you measure about the Higgs with what you know or you think you know about the Higgs. So this could be about 10 years after the end of the LHC. And then after that, the idea would be maybe to build a new LHC, kind of like a super LHC, whose energy would be about 7 times greater than what we have now. And this would be, its goal would be to study the nature of dark matter in the universe. Now, if you remember the very early video that I showed you of the protons colliding and in each successive accelerating in each accelerator, and then we stop at this accelerator here, which is the LHC. Well, the next one, if we build it, it's called a circular collider. It would be something that would be about 100 kilometers, and this is like a proposed place to put it. So 100 kilometers, and it would host first the Higgs boson factory, and then potentially afterwards this super LHC. And there are already international collaborations that are proposing new detectors to build this accelerator. So it's really a very exciting future for particle physics. Very long term. I'm going to be retired before they ever get around to building this, but it's fun to think about it and it's fun to plan it. So I just wanted to thank you very much for inviting me. I've dropped here a few links that you can get from the website of the conference, including for fun. There's actually a Google Street View of Atlas. You can go wander around the Atlas cavern with Google Street View if you'd like to see what's happening inside there. So thank you very much, everyone. And I hope that you enjoyed the talk today.
Thank you very much for this wonderful talk. We do have a few questions in the chat here, and eventually people can write some more. The first one is about these pictures taken with the Atlas detector, and how and where these pictures are stored actually.
Yes. So so if you go to the Atlas public site, actually you'll see a lot of these pictures that you're more than welcome to download and have a look. Okay, just struggling to find. I think I have to go backwards like this instead. There we go. Yes. So all the colorful things that you see on these pictures, this is our rendition of what we think it would look like. So it's not really a camera, even though I'm taking a picture of what's happening. What we collect is the information is the particle is the detector. As the particle goes through the detector, it leaves little traces of information. So if you remember when you were a child, maybe you played the connect the dots, right? And you can follow with a pen the dots. So it's essentially the purpose of the detector. So every time something goes through the detector, it sends a little information. And from that information, we're able to reconstruct in a diagram like this, where the particles came from. And then we just, make a visualization with a computer so that it looks, a little bit nicer. So these are actually exactly the same information, the same data that we use to study. It's nothing different than it's just like one of the many events that we would do. For example, recently we did a publication on the 4-top quark production as an observation of that, which was very exciting. It was the first time. And this information is actually, so there are a few places where this information is stored, but once we take a collision and we think it's a good collision, it's a useful collision that we think we can do real science with, first it gets stored at CERN, but then it gets distributed around the world. We have this distributed computing where members of our collaboration, their country would have a facility where they would store some of that information, and any Atlas member can have access to all of this information. And the beautiful thing about it is completely seamless. So I don't even need to know where the information is stored. I just know it exists somewhere in the universe or somewhere on this planet, I guess maybe. And when I try to analyze this, I just say, oh, I need this piece of information, and somehow it almost magically appears on my computer. It's very seamless, but it is stored in computing sites around the world.
Thank you. And then we have a second one, a more political one. Mm-hmm. Why didn't the LHC experiments or their representatives win the Nobel Prize as well?
Yeah. Well, it was fun because the day that the Nobel Prize was announced, we were actually in a collaboration meeting. We were meeting in Marrakesh, Morocco. And in fact, we interrupted our meeting so we could live stream the Nobel Prize. Unfortunately for us, we'll probably never get a Nobel Prize. And it's kind of built into the terms of the Nobel Prize that they can never give it to more than 3 people at a time. So had they wished to give it to Atlas or the sister experiment, CMS, who also saw the Higgs boson at the same time, they would have had to pick 3 people. And yeah, it's politically very difficult to do. So maybe it's also, in some sense, the people who predicted this. I mean, they went on a limb, right? I mean, they predicted this, and then they waited for 50 years basically before someone saw it. So they're the ones who received it. We did get a good recognition, though, because if you read the Nobel Prize citation, it says it's given to these people for having predicted this. And it does say in the citation, as discovered by the Atlas and CMS collaborations. So we didn't get to go to Stockholm. We didn't get medals or anything like that. But we did get a good mention there. So that's why we couldn't get the Nobel Prize. There's only one type of Nobel Prize that can go to large groups, and I think it's the one that came a little bit later on, right? That's given to, for example, to humanitarian groups. Yeah.
Thank you. And then we have another one. How do you distinguish these hypothetical dark particles from the ordinary ones that reach the detectors?
Yeah. That is the biggest challenge. Here we are counting very much on the fact that we understand quite well this other type of dark matter. Maybe I just go back here to here. Here we're counting on the fact that we understand very well this other type of dark matter, the neutrinos. So neutrinos have been known for quite a while. We've measured the processes where we find neutrinos. So here, there's a few examples here. This is a W and a Z, right? These are the 2 carriers of the weak force. So we understand pretty well those processes. We've measured them quite precisely, but it's still an induction in the sense that we build in our knowledge into this. We say, okay, this is what we think we know about the neutrino. And then we have to take this away from what we observe, and then we're looking for the differences between that. And that's why anytime we make a prediction about something, for example, the neutrinos, we can never make just a prediction. We always have to say, we predict this with some sort of uncertainty associated to it. And that uncertainty is supposed to cover our ignorance related to that particle. So that's how we do it, right? We have to know very well those particles, and then we subtract it from what we see, and hopefully, if there's something left over, then it's something that we don't know about.
Okay, thank you very much. We have still another one, and I would like to invite people to write if they still have some more. The next one is, what is the benefit of colliding electrons and positrons instead of protons?
Yeah, so that's a great question, actually. They both serve a purpose, huh? So let me just go back over here to my distance scales, because I think it'll explain it really well. If you remember the atom here, I went through the size of the nucleus, the proton, and the quark, but for the electron, I don't know if you noticed it, but I went straight down here for the electron. The electron, as far as we know, has nothing inside of it. It's a pure object with nothing inside. So the beauty about electrons is that when you collide an electron with an electron, you're colliding something that has nothing inside with, no substructure inside, with something that has no substructure inside. So the collisions that come out are actually really beautiful. They're very, very clean. When you're colliding a proton on a proton, actually, you never really collide a proton on a proton. What you do is you're colliding something inside the proton, for example, this green quark, with something inside the other proton, which might be a blue quark, for example. And so you have, you're striking 2 things that are inside the proton, but all the other stuff in the proton is there as well. And so when you do the collisions, it's much messier because you're colliding a quark on a quark, but then you have all the other stuff left over. So now you might say, well, why do you ever bother looking at protons? Because electrons are so much cleaner, right? And yeah, they are really cleaner, but they have the characteristic, because electrons don't have a very high mass, that if you make them go around in a circle like in an accelerator, the higher the acceleration, like the faster you make it go, the more energy it loses. So it's very hard actually to make an electron go really, really fast. And if you wanted to go faster, you have to put in a lot of technology behind it. A lot of it we don't actually have. Whereas the proton, when it goes around the accelerator, actually it doesn't lose a whole lot of energy. So you can make these protons go really fast. So in fact, you need both types of accelerators. Let me now go to the strategy at the end, which is a really clever strategy if you think about it. So let me go over here. There we go. So you need both. What you do is you have a proton collider like the LHC, so that you can go to very high energies, and then you can quickly see is there new science? If I collide protons together, do I see new particles? Is there something really interesting to see? And then if there is something interesting to see, like the Higgs boson, you go, oh, wow, that was really nice. But the Higgs boson, when you make it, because you're colliding protons together, it's not as nice a collision. It's kind of all messy because of all the insides of the proton. What you then do is you go and build an electron-positron collider, which is very clean, point-like particles. And there you have such beautiful, oh my goodness, they're so beautiful, these event displays. They're just so clean that to understand the science behind it is so straightforward. So you build a proton machine to go look for new discoveries. Once you see it, then if you really want to study it properly, you actually build a electron-positron collider, and then you measure that new new particle really well. So that's why I want to do the Higgs. But then, of course, eventually you want to go back to the next proton accelerator, because now you want to go to even higher energies to see. So one kind of guides you along the path, and then the other one makes you just do very precise measurements. So that's why you actually need both. And I think it's time. And in fact, before the LHC, there was another collider in the LHC tunnel, which was called LEP, and it was an electron-positron collider. So now I think it's time to go E plus E minus, and then you can go back to proton and do that for 200 years.
There are two follow-up questions on that one. The first one is, but what do you expect to see with electron-positron collisions if they have nothing inside? And the second one is, where to get positrons from? There's no positrons in hydrogen or whatever.
Yeah. So the first question is, if you remember at the very beginning, I mentioned matter, energy, matter. So when you collide the electrons together, they create energy. So the electrons don't exist anymore. So they were electrons, then they became energy. And then that energy becomes the new particles, like the Higgs bosons, for example. So it doesn't really matter that there's no substructure on the inside. I only want to use them to make energy. So that's why it's actually an advantage somehow to have these point-like particles, because it just goes straight to energy. There's nothing else left over. And you have to remind me, what was the second question?
Where the positrons come from?
Yeah, positrons. So interesting, yes, because nature is made from these atoms, which is protons, neutrons, and electrons. Actually, you can make positrons quite easily in a lab if you have photons. Photons can turn into an electron-positron pair. So if you have photons and you have to have them in the right circumstances, they can actually turn into an E plus and E minus electron and a positron, which you can then use to do the collisions with. So you can make them. They don't exist really in nature just like that, but you can make them in the lab quite easily.
And then we go to a more technical question, asking about the challenges of Philomi LHC and disk space. How can if Atlas can already deal with the huge amount of data to be produced.
Yeah, it's a real challenge. And in fact, one of the big things that we were working on right now, actually in the last 2-3 years, is first of all, we need to reduce the amount of space that we need to start off with. Okay, the short answer is if we use what we have right now in terms of the software and the computing, and if we were just to go use it at the HLHC, the answer is no, we cannot do it. So we need to be smarter about everything that we do. So now we go through, you write software, you write, piece of computer code to do different things. For example, to trace the path of a particle, this connect the dots, etc., and to store the information. And what we've done in the last few years is we just go back to all of this software that we wrote a long time ago and we rewrite it from scratch, where we really start thinking cleverly about how we do things. In the past, maybe we weren't so constrained about, how long it takes to look at one event, to process an event, or how much space we had. For a long time, it was every 18 months you were doubling the amount of space you could get for the same amount of money. Something like that. Those days are kind of over. So we've started to be much smarter about how we write the software. And that's been an enormous challenge, a really good challenge, actually. I think a lot of people really enjoy that. People have been learning a lot about how to write software. So that's one of the big challenges, has been to try and sort of rewrite what we have to make it much faster. I don't know if any of you are into computing, but what we do now is like we process events serially. So, you look at an event, you study its properties, then you move to the next one and you look at the properties, and then you move to the next one, look at the properties. And now we've been writing code so you can have multiple threads, in the sense that you can look at different parts of different events simultaneously, whichever comes fastest, instead of having to be like a train. Basically, you can sort of mix and match information. Of course, you have to gather things together at the end to still have the information properly. For disk space, we're starting to think about how can we, well, you see, we've been doing analysis now for a long time, right? We've been doing since 2010. So now we have a better idea of what we really need to do our analyses. So we're trying to use data formats that are much smaller than before, less information. We still have some, we do make some data files, which has all the information, so we can always look at it. And we always store the basic information. There's always 2 copies at least somewhere in the universe of all the information we took. But the information that we actually use to do our analysis is starting to be much smaller. So because we know what we need to do our analysis now. So it's a huge challenge, and the short answer is what we have now would not work for the HLHC. So we're really working very hard at reducing our disk footprint, making the CPU much more efficient, and doing this multi-threading instead of doing events in series, basically.
Thank you. And finally, we have a last one, at least so far, about your slide on dark matter. And the question is, what did Louise see that made her to be sure about the existence of dark matter? What was observed, basically?
So what she was able to observe, now she didn't observe dark matter. Nobody has really observed dark matter. But what she could do, now did I go too far? Yeah. So what she did is she looked at the galaxy. She could make a good guess as to how many stars there were in this galaxy. So she knew basically how many stars. She can make a good guess of how much each star weighs. So she had a pretty good idea of not only the mass of the galaxy, but how things are distributed. Where's there more massive parts? Where's there less massive parts? And so what she had to do was just measure how the stars were going around the center of the galaxy, depending on where you are in the galaxy. And so really what she didn't see the dark matter. She just saw that the properties that she measured of the stars were not what she expected. mean, she expected, for example, a star out here to be going fairly slowly, and what she actually measured was it was going very fast. And then everything else after that is kind of a supposition, right? You're saying, okay, what could account for this difference, right? And it's a big difference. And that's where this idea of well, maybe she did look for all the matter, but maybe there's a lot of matter in that galaxy that is not luminous. She couldn't see it with her eyes or with her equipment. And if you were to inject that mass in there, then it could describe what she actually saw.
And now it's up to us to find it.
Yes, indeed, it is up to us to find it. Lots of possibilities, and we are looking for it. Nothing so far.
So I think we are reaching the end, and everyone is thanking in the chat for this wonderful talk. I would like to also thank you, and it was really a pleasure to be here and to listen to you and to all these very nice explanations. Thank you everyone for following us on the streaming via YouTube, and that's it for now. So
thank you for coming, everyone. It was a pleasure to be with you today. I wish I could have seen you in person. Maybe some other time.
Some other time soon.
Yeah.
I'm optimistic.
Mm-hmm.
Okay. Thank you very much. And we are finishing now. Goodbye and good night to everyone.
Thank you so much. Really wonderful.
Oh, I'm glad you enjoyed it. I love giving talks like this. It's fun.
The language the approach was perfect for people that are not physicists. So I really enjoyed it just as an attendee, as any other person.